So in this first part of the experiment, our job is to torture a dolly. So in question 1, they tell you put the doll on the back end of the cart and then yank the cart forward quickly and describe what happens to the doll. So like that. It's probably most useful in this first question to specifically describe how the doll moves relative to the table rather than to the car. In the second question, we don't want the doll to fall off the cart, but we are going to smash him into a brick wall as hard as we can. So like so. Again, describe what happened to the doll, and it's probably very useful in this question to talk about how the doll moved relative to the car rather than to the table. The third question is exactly like the second, except that this time we're going to give Dolly a little seatbelt. So again, we'll smash him into a brick wall. Again, describe what the doll did and relative to the cart. The fourth question is where you explain the physics of these three cases. So they specifically tell you to think about inertia, the idea of resistance to change. It's also incredibly useful when you're trying to describe these three cases to think about Newton's first law. So Newton's first law is that a body at rest tends to stay at rest unless acted on by a force, and a body in motion tends to stay in motion unless acted on by a force. That one law describes these three cases. You just need to think about how. So when you're answering question 4, think about inertia and think very carefully about Newton's first law. So this is the equipment we use for the next part of the experiment. We've got a cart on a track, and we're going to exert forces on this cart, and it will accelerate, and we'll measure that acceleration. So first things first, anytime you use the track, the first thing you do is level the track. So you stick this guy on here and adjust the ends of the legs on the track to make sure that everything is nice and stable and level. Now, as I said, we're going to exert forces on this and then measure the acceleration of it. So we're going to use the acceleration program you've used before. I'll give you a quick refresher on that in a moment, but let me first show you how you physically do the experiment. So the acceleration in our case comes from this mass hanger. Might be a little hard to see, but there's a pulley at the end of the track here, and you're going to dangle the mass hanger over the pulley and then hook it onto your cart. And then, as you see, if I release the cart, the mass of that hanger accelerates it down the track. So let me show you how you do this one. Is you'd pull this guy back, press collect on the program, and just release. And once you're done, as normal, you will fit a straight line to your velocity time graph in order to get the acceleration of the cart, because we need that. Now, we're going to do 4 cases with the track, and we're going to compare the second case back to the first case, the third case to the first case, and the fourth case back to the first case. So everything gets compared to this graph that we just made. So this is called the control, and all the other 3 trials are going to be compared back to the control trial. So you need to print out 3 copies of this graph for every person in your group, because it's going to be pasted in 3 different locations of your lab manual, and then you'll compare a second graph always back to this first graph that you made. So print out 3 copies for everybody in the group. Let me show you the second trial now. You take this guy, and you flip the cart upside down, and you stack the masses on there. One moment please, my mass hanger fell off. So the mass hanger is now still dangling off the end of the track, and I've got the cart flipped upside down. And again, you make a graph of this. Now obviously this is going to be a pretty boring graph, but we should be able to understand the physics of this. We've still got the cart, we're still exerting forces on it, and there's a reason why our acceleration is going to be pretty close to 0. So this is an important case that we're going to compare back to the second one. Now there's 2 more trials that we're going to do, but before we get to that, there's question 6 in the lab manual. So I'm going to pause here. I'm going to give you the brief refresher on how to use the acceleration program, and then I'm going to tell you how to do question 6, and then I'll show you the next 2 cases that we're going to do using the track. So now let's look at that acceleration program. So we go to the 1100 folder, and we open up acceleration. So you've seen this before. And It's fairly simple to use. As you recall, you pull your cart back to the location you want it to be, you press collect, and then you release it. Now, this stuff over here is just because it bounced off the end of the track. We only really care about this section of the data. As before, when you've used this program, the scale is way too big for us to actually see the linear part. So again, to fix that, you click on the highest number, and then you can type in whatever you think is appropriate, like 0.5. And again, for the negative one, I'll go minus 0.1. And that was a little too big, so I'll go with 0.7. So that gives me the linear section of the data here that I care about. And as usual, you pick a section of the data that looks pretty linear, and you fit a straight line to it. And then we can arrange that so it looks nice and print it off. The manual does say that you have to print off both graphs, but I'll let you know that it's only the second one that's actually worth marks. Now, the manual tells you that after you've printed it in and pasted it into your book, you also need to state the acceleration. That means write it by hand with its units. You do not need to write an uncertainty on it yet. So just write down the acceleration from this with its units by hand on your graph. And remember, this first case, you need to print out 3 copies of the graph per person. So now I'm going to talk about question 6. And I've got this zoomed out for a reason, though, because I want to talk a little bit about question 5 again. So let me scroll back. You remember that question 5A was where you had the cart right side up, and it accelerated down the track. Now remember I said you had to print out 3 copies of that graph per person in the group. So where do the 3 copies go? The first copy will go here, and you're going to do the second trial with the cart flipped upside down and paste its graph down here and compare the two. But of that first graph, the 3 copies, 1 copy goes here, and the second copy, if you scroll down to question 7, second copy gets pasted in here, and the third copy will be in at the beginning of question 8. And in all 3 of those cases, you'll have a second graph on that page, and you'll compare the 2 to each other. So you'll look at the acceleration values on the 2 and see what happened. So question 5, 7, and 8 is where you paste in those 3 copies of the first velocity time graph. So now let me talk about question 6, and I'll zoom in a little so you can read this better. So in question 6, the first part of it says, when a force acts on an object, what happens to the object? So your answer should be some variation on, well, it accelerates. That's not the full answer, but I'll let you come up with the appropriate wording. That's the gist of it, though. Now, they don't leave space for you to answer that first question, but it's worth marks, so squeeze it in somewhere, as you do need to actually answer that first question to get full marks on question 6. Once you've done so, then they want you to expand on your answer by talking about 3 other cases you've looked at so far. So you want to say how your answer to this first question helps illuminate what was going on in questions 3 and questions 5A and B. So what was question 3 again? That was specifically the doll on the cart wearing a seatbelt. So we're talking about forces acting on an object. This is the case where the doll had a seatbelt on it. So think about that and talk about how a force acting on an object helps you understand that third case. Cases 5A and 5B were the ones on the track that you just did. So cart right side up, accelerating down the track due to the mass hanger, and the second one is the cart upside down, where it didn't move down the track. And again, think about forces acting on an object and what they do. So this all has to do with Newton's second law, F equals ma. So you explain how that law helps you understand these 3 cases and what sort of behaviors you saw in them. Okay, now we're ready to do the third and fourth trial using the track. So what we do in the third trial is we're going to take 50 grams off of the cart and we're going to put it on the mass hanger. Now the mass hanger all by itself is 50 grams, so we've doubled its mass. And if you think about it, what we're doing is we kept the mass of the entire system the same, but we doubled the force that's going to accelerate it. So mass is the same, force doubled. And we're going to compare the acceleration values we get for this case back to the very first case. So you just dangle that, mass hanger over the pulley, and as before, release it, allow it to accelerate. And that's a little violent, so I caught it. But you would capture that graph, fit a straight line to your VT graph, and get the acceleration for this system, where the mass is the same, but the force has been doubled. That's your third trial. The fourth trial, you grab your mass hanger again, take that 50 grams off, but you're going to take 600 grams off the cart and just put that 50 there. And what this does roughly is that we've roughly halved the mass of the entire system, but we're going to be accelerating it by the same amount as we did in that first case. So in this case, we've got the same force as that first case, but we've halved the mass. And so again, you would start the program running and just release it. Let it accelerate, and you'd measure the acceleration of this fourth case, where the mass was halved, but the force was the same as in the first case. So in all four cases, or pardon me, in the last three cases, you're always going to compare back to the results you got in the first case. So now I'm going to explain very briefly how you answer questions 9 and 10. So question 9 is all about those last two cases we studied on the track. So question 9a says, if we double the force on the system, but keep the mass the same, what happens to the acceleration? So you go back to question 7 and you write down your acceleration values, actual numbers, and look for an obvious proportionality. So was the acceleration twice as big, half as big, 4 times as big? When you doubled the force and didn't change the mass, what happened to that acceleration? So you should answer this based on actual numbers from your graphs. Same thing for question B, except you're looking at the data from question 8. So if we half the mass of the system but don't change the force, what happens to the acceleration? Again, write down your numbers, identify obvious proportionalities, and then explain what happened to the acceleration when you halved the mass but didn't change the force. Question 10 is then where you bring it all together. They say, how does acceleration depend on force and mass? So you're going to write down a formula that will look suspiciously like something you've seen in class, but you brought it all together based on your data. You write down that law that relates acceleration to force and mass, and then you need to explain how that law helps you explain all the results from questions 1 to 9. So the whole lab so far. So to get full marks for this, you need to talk about all 3 cases with the doll and all 4 cases on the track, and say how this law you came up with helps you explain what you saw in all those cases. So 3 cases with the doll, 4 cases with the track, talk about all of them. So here is the last of the equipment we're going to use in this experiment. So we've got 2 carts. They've both got wireless sensors on them, and I'll show you in a moment how to get those 2 wireless sensors communicating with the computer. I'll show you on screen. But for now, let me just show you how you physically do the experiment. These guys have bumpers on them. So this one's got a spring bumper, and this one's got also a little bumper, though it's not a big spring. But we're going to crash these into each other, and then they can actually detect how much force they exert on one another. So we're going to use a program called Car and Truck, and one of these is going to be the car, one of them is going to be the truck. Which is which? Well, we take a mass, we stick it on one of them, that's now the truck. So this is a car, this is a truck, and the experiment consists of bouncing them off each other in a variety of ways and capturing that on the computer screen. So the first question tells you to start with the car at rest and run the truck into it. So that just means you'd do this, and you'd capture that on screen. I'll show you how in a moment. The second one consists of the car moving and the truck stationary initially, so like that. And then the third case is you have them both moving, so you'd bounce them like that. And in all 3 of those cases, you'll capture a graph, print it out, and then at the end you answer questions based on it. So now I'll show you how to use the program itself. Okay, now I'll tell you about the Car and Truck program. So as usual, go to the 1100 folder, and in there is a program called Car and Truck. Open that up. As with the Uniform Circular Motion Lab, we're using wireless sensors here. So it may be that the technician has already opened this program for you and made sure that the program and that the computer and the sensors are talking to each other. If not, then when you open it up, you'll see this dialog box, and it'll be up to you to get everything set up. So first thing you do is make sure that your two sensors are turned on. Also, if they're plugged in, you can unplug them. They were just charging up. So make sure they're turned on and unplugged, and look at the side of your sensors and make sure that you know what the names of the two sensors are, because we've got lots of them in the room and the computer may find somebody else's sensors as well. So once you've got everything turned on, you click Scan for Wireless Devices with this button here. Wait a moment. You may need to scan more than once, so if it doesn't find any sensors, it will pop up a box that allows you to rescan. If it does find something, you'll see this dialog box. Now, it's only found one of my sensors. That happens sometimes, so if that happens, click Rescan, and hopefully it'll find both of them the next time around. In fact, it might find more than just your sensors. It might find the sensors on other desks as well. And I'll need to rescan again. Like I said, this is pretty common that you'll have to do this more than once. So hopefully it's going to find both of my sensors very soon. And this time it found them both. So I click those two, hit OK. Program thinks for a moment, and then it makes it so that I can take some data. So it will show me this collect button when it's ready to take data. Now with this experiment, it's a really, really good idea to zero your equipment first. So right beside the collect button, there's this zero button. You click this and you'll hit OK on the defaults, but before you do that, make sure that the two spring bumpers are not touching each other or anything else. So they should just be untouched by anything. And you click 0, hit OK, and that calibrates your sensors such that you'll get the most accurate data. So now you're ready to take some data. So if I click collect, it does this annoying thing where I have to say erase and continue, so don't panic if you see this. And now I can start bumping my two carts into each other and see what happens. So the green line is one of the sensors, the force that it's detecting, and the red line is the force detected by the other sensor. So you can see here that for what I was doing, they exert equal and opposite forces on each other. So you can now do your experiment, the three cases, one where you run the car into the truck, one where you run the truck into the car, and one where you run them both into each other. So you'll make three graphs, and you can bump them against each other more than once like I've done, or just do it once. That's fine, either way. So you get your three graphs, and then in question 11D is where you talk about what you've seen. And this is all about Newton's third law. So for every action, there's an equal and opposite reaction. You look at your graphs and see whether or not the results you've seen are in keeping with Newton's third law and discuss it. Okay, on the last page of the experiment, there's question 12, and I'm just going to give you a very, very minor hints on how to do this one. So in each of these cases, what it is they've got a little diagram and a force that's being exerted. So for example, the person kicks the ball, they push on the ball, or the person pushes on the floor because they're standing on it. And in each of these cases, you want to name the reaction force and also draw in the vector. So you would draw a little arrow on this diagram showing me which direction the reaction force points. You also need to name the reaction force. I don't actually require you to come up with an official name. You can just describe in words to me what the reaction force is. So person pushes on the ball, what does the ball do back to the person? Or the person pushes on the floor, what does the floor do back to the person? You can just describe it in words. I will warn you that the third one is actually quite tricky. So I'm just going to give you a very modest hint in the way I'm wording this. The earth pulls on the person, what does the person do back to the earth? Think carefully about that one. That's the only hint I'll give you.